Alcohols can be prepared via reduction of carbonyl-containing functional groups, such as ketones or aldehydes. In this example, we see cyclopentanone being reduced to a secondary alcohol. And the reducing agent is sodium borohydride. There's also an example on this slide of a aldehyde getting reduced to a primary alcohol. And the reagent that's shown is lithium aluminum hydride. Both of these reducing agents, sodium borohydride and lithium aluminum hydride, are common reducing agents, and both are capable of reducing either a ketone to a secondary alcohol or an aldehyde to a primary alcohol. The big difference between the two is in their reactivity. Sodium borohydride is less reactive, but still reactive enough to reduce ketones and aldehydes. Lithium aluminum hydride is more reactive and will also reduce both ketones and aldehydes. Notice the solvents, the way it's written over the arrow for sodium borohydride. This is typically done in a polar protic solvent, such as water, methanol, or ethanol. But in the case of lithium aluminum hydride, you notice there are steps 1 and 2. And that's because lithium aluminum hydride is more reactive, and if it was exposed to water, it would react with water, which we don't want. And so typically, this reaction with lithium aluminum hydride is done in a polar aprotic solvent, and then water is added after the reduction has taken place to quench the reaction. Let's look at the structures of sodium borohydride and lithium aluminum hydride. You can see that they're very similar, the main difference being the counter ion, which really has no effect on the reaction, and also either having boron here or aluminum. But they're both negatively charged and considered hydride donating reagents. And again, they are both capable of reducing aldehydes and ketones. It's just that lithium aluminum hydride is more reactive than sodium borohydride, and so we need to take more precautions when using that in the laboratory. The mechanism for either reduction with sodium borohydride or lithium aluminum hydride would be similar. So let's look at an example. If we look at cyclopentanone and its reduction, we'll use sodium borohydride. It has the advantage that it's less reactive, so it's not, won't react with water. So when we can get away with using it, it's definitely an advantage. So it's a good hydride donating agent, and so H with 2 electrons, which is considered hydride, can go ahead and attack the electrophilic carbonyl carbon. At the same time, we need to show a resonance arrow, electrons moving up to the oxygen. So now we've essentially reduced the carbonyl carbon, and the oxygen is negatively charged. So I mentioned the solvent for this reaction is either water or some sort of protic solvent like methanol or ethanol. And so the proton will be exchanged from that solvent. to the alkoxide, producing in the end the secondary alcohol product. And again, the mechanism is really analogous if you had used lithium aluminum hydride instead of sodium borohydride. We can also produce alcohols through the reduction of a carboxylic acid or an ester. Both of these require the stronger of the reducing agents, so you absolutely have to have lithium aluminum hydride. In this case, sodium borohydride would not be strong enough to reduce either a carboxylic acid or an ester. And the product in both cases is a primary alcohol. The mechanism of the reduction of a carboxylic acid with lithium aluminum hydride will be covered in a later chapter. But we will go over the mechanism of the reduction of an ester with lithium aluminum hydride. Notice that it says excess lithium aluminum hydride, and that's required because we will need at least 2 equivalents of the reducing agent to produce the product in the end. Let's look at the mechanism. So if I just take an ester, in this case I'll draw what's called a methyl ester, and we'll draw some lithium aluminum hydride. Again, I can leave off drawing the lithium cation because it's just a counter ion and not involved in the reaction mechanism. The first step, similar to the reduction we looked at before, is addition of hydride to the electrophilic carbonyl carbon and the resonance arrow. We've added hydride and formed this negatively charged intermediate. This intermediate is still reactive because there's a potential leaving group attached to this carbon. So if we push electrons back down to reform a double bond, it's possible to kick out this oxygen, where it's not possible to kick out a carb anion. We can have an oxygen with a negative charge be a leaving group. It's not considered the best leaving group, but it's suitable to leave in this particular reaction. After we kick that out, we've produced an aldehyde, which is an intermediate in this reaction. And then we've also produced the alkoxide, which is methoxide in this case. The aldehyde carbon is still, carbonyl carbon is still electrophilic. So that's why we needed a second equivalent. It would not be possible to isolate the aldehyde. We need to have enough LAH present to also reduce this, otherwise we'll end up with a mixture of products, which we'd like to avoid if possible. So because the aldehyde carbonyl carbon is still electrophilic, we can have a second addition of hydride. This produces an alkoxide, and there'll be a second addition of hydrogen here, which we typically don't draw in once it's regular hydrogen attached to an sp3 hybridized carbon. So notice the product at this point are 2 alkoxides. And then in the second step, we need a workup, and some water or acid will be added, and that will function as a proton source for the alkoxides. And this won't occur until we've quenched the reaction, because remember, water is not present initially, otherwise it would just react with lithium aluminum hydride in a proton transfer reaction. So in the end, we get primary alcohol product and also some methanol. So we get 2 alcohols when the starting material is an ester.